All right. Today I would like to talk really briefly about the Gdb quiz and just mention a few things about the memory mapping if you haven't finished that or if you're not sure what the point of all that was. So I want to look at that a little bit. There's no ODPs until Monday morning. There'll be an ODP. I'm going to post it over the weekend, but it's not going to be due till Tuesday, so technically you don't have to start it till Monday. But if you want to look at it ahead of time, it'll be posted on the weekend. So then I want to go and I want to look at some pseudocode for queues and stacks and implementing them using arrays and implementing them using lists. And probably we won't get to it today, but eventually we're going to move in and talk about applications of stacks and queues. And I'll give you some motivation for why these are useful structures. Tomorrow we will talk about PA3 and go through that in the usual way. So any questions before we start? So let's take a quick look at the Gdb quiz from yesterday. So we were debugging this program G1, and I've got list code because I've got permission for the file, but if you say list, it doesn't show you the code, right? So you have to figure out what's going on by looking at the memory. And so one thing it asks you to do is look at the address of data 0, and it tells you data 0 is stored at 60, 10, 60. So let me make a memory map as I was suggesting yesterday. So we'll start at 60, 10, 60. And we know our structure is 32 bytes, so I should have 32 numbers up there, but I'm not going to go through the whole thing. I just want to show you the start of this. So there's different fields to this structure. And one field was x, so we can print the address of data bracket 0.x, and it tells us it's 60, 10, 60. So x begins right here. And if we print size of, assuming we spell it correctly, if we print size of data 0.x, it tells us x takes 4 bytes. Now it could be that it's a integer, it could be that it's a floating point number, it could be an array of 4 characters. We don't know what x is, except that it's telling us it's an integer star. But it takes 4 bytes, right? So these 4 locations correspond to x. Alright, so I'm going to cheat. Use this to remind me what the fields are. Okay, so there's a field called C1. So if we print the address of data 0 C1, that's stored at 64, so that's starting right here. And if we print the size of C1, that's 1 byte. So this location is used to store C1. And there's another field, C2. So C2 starts at 65, that's the next location. And the size of C2 is also 1 byte. And so we're creating what's called a memory map, a picture that shows us how memory is being used, in this case, for something that is a MyStruct. Okay, well let's print out one more, or 2 more. The address of y is 68. So y starts right here at location 60, 10, 68. And the size of y is 4 bytes. this is being used for y. And F1 starts at 6c. And the size of F1 is 1. So here's F1. And F starts at 70. And the size of F is 8. And so on. We could do Z also. And so for question 10, the question was, what's the address of the first unused location? Well, that's 601066. Right, that's the first place where things aren't completely packed in. Because there's nothing being used here or here. And there's also nothing being used in these three locations. And if we look further down, we'll see another 4 empty locations. So we have a total of 9 bytes that aren't being used. And that's the difference between the 23 bytes that you calculated you needed and the 32 bytes that you were told by size of was actually reserved for a struct node. So one moral of the story is when you create a structure, the pieces of your structure aren't necessarily packed together in memory. There may be gaps between them. And normally this doesn't concern us. It concerns the compiler greatly. It concerns code that's going to use that structure. But to us, if we want the field called F1, we just say, you know, variable name arrow F1 or variable name dot F1. We don't care if it's here or if it's up there or if it's down here or if there's something above it or not. But it's interesting to note that these things could be packed into 23 bytes, and instead the system takes 32 bytes. So why are there gaps? Why did Y start down here instead of starting up here? Any ideas?
Overflow?
How so? Could be related to
C1
that.
and C2 could need more space than they are allotted.
Yeah, that's a good answer. It could be useful to have space here if this was an array and the array overflowed, right? You could have a little buffer here. So that's one possibility. Anything else?
Integers have to be 4-byte aligned?
Yes. Do you know why?
I don't remember.
Okay. So it turns out that when we think of memory, we just think of a big long collection of 16 billion bytes. If you've got 16 gig of memory in your computer, just 16 billion bytes. And each one has an address. That's not how memory is actually organized in the hardware. It's usually 32 bytes maybe across or 64, and we have multiple rows. And for technical reasons, when you get into the actual design of a memory subsystem and the hardware that's used to read and write to and from memory, it turns out reading a single byte takes almost as much time as reading 32 bytes. And writing a single byte takes about as much time as writing 32 bytes. Because the system is designed to efficiently manage large memory transfers. So things are done in these larger block sizes. So it turns out that if I stored Y like this, so these are the 4 bytes of my integer Y. Turns out reading these 2 bytes takes the same amount of time as reading this block of 4 bytes. And if I want to read these 2 bytes, I have to read this block of 4 bytes. And if my integer is split between this set of 4 bytes and this set of 4 bytes, I actually have to do 2 memory operations at the hardware level. I have to say, okay, give me this block, give me those 2 bytes, ignore those, grab this block from memory, give me those 2 bytes, ignore those. Okay, take these and shift them over to the left 16 spots and then combine it with these to give me a 32-bit number, and it's a really expensive operation, and it kills your performance. So the compiler knows this, and it does things accordingly. It says, okay, this is an integer. I'm just going to waste these 2 bytes of space, and I'm going to start my integer right here where it's word aligned. Okay, a word being 4 bytes in this case. But sometimes it wants it to be aligned on an 8-byte boundary. Could be bigger. And it's a function of the architecture of the CPU, the architecture of the memory subsystem. Right? It depends on the hardware. On an old Intel 8080 processor, this is a non-issue. On a modern processor, it's a critical issue. So the hardware and the software and the architecture of the CPU and the operating system setup, these things are not independent entities. They can be, but you get a really poor performance out of it. They're kind of designed with an understanding of each other in mind, which is part of why if you're a computer scientist and you're learning how to program, you still got to take Engineering 270 and deal with the hardware aspects, because it's harder and harder to ignore it as we go forward. Everything's kind of tied in with everything. And that's good, that's opportunity. That's how we can make processors that really fly.
What could you do to make F1 be up there with C1 and C2?
You know, a decent compiler might just go ahead and do that. And it's possible that the compiler considered that and realized that when you malloc, you're always going to get a multiple of 32, I believe. And so you've got the extra space anyway, and so just decided to keep it in order. But I don't know. If you pull down the source code for GCC, you can probably figure it out. That'd be a fun quiz question. Reverse engineer GCC. It may be that when I define the struct node, if I put F1 right after C1 and C2, that would be all it takes. So there's G1, and I think if you put character F1 right after C1, C2, it'll put it up there in the beginning, but I wanted gaps in there. And so that finding where I changes to 5 is like, even if you got the source, you probably can't figure it out. It's easier to figure out how to do watch points. All right, so continuing with queues. So let's work with a smaller queue so we don't need such large examples. So we're going to have a queue with 5 elements. And we'll just call this Q. And remember, we have a head and a tail we have to keep track of, so I'm just going to call those H and T and initialize them to 0. And so we insert at which end, tail or the head? Tail. We remove from the head. So let's do some operations and see what happens inside this queue. So let's insert digits of pi. So we'll insert a 3. And where should the 3 get stored in this array? Got a 20% chance if you guess. Okay, which is 0. So the 3 goes right here. Okay, that's what the tail equals 0 is telling us. So we insert a 3, that goes right here. And what do we have to do after we insert? Increment the tail. Otherwise, the next time we insert, we'll also put that there and it'll wipe out the 3. So we'll increment the tail to a 1. Okay, let's insert a 1. Again, look at the tail. It's equal to 1. Store our number at index 1. There's our 1. And increment the tail. Let's insert a 4. exactly the same thing. Tail's equal to 2, store it at index 2, increment the tail. So we've got 3 examples of insert. That's enough for us to write some pseudocode. So insert the number n, q bracket tail equals n, tail equals tail plus 1. All right, let's do a remove. So if we say remove, what's the first thing we should remove from the queue?
Where the header is.
Yeah, where the head is. So right now, before we say remove, head is equal to 0, tail is equal to 3. So that's what our queue looks like. We remove from the head of the queue, right? That's the cashier. These are the customers. First one in line is the 3. So this should give us a 3. And then what adjustment do we make after we remove? Increment the head. Otherwise, if we remove again, it'll still give us a 3. So change the head to 1. And now the head's sitting right here. Bless you. If we remove again, look at the head, it's 1. Tell us what's at index 1. That's a 1. Increment the head. So now our queue looks like this. So pseudocode for queue removal. So see what's stored at the head. I'll save that in a temporary called return. Increment the head and return that return value. Good so far? Okay, let's do some more inserts. We'll switch colors here. That looks like the same thing. So let's insert a 1. So insert says, look at the tail, that's equal to 3. Set Q3 equal to 1. That goes right there. Increment the tail. Tail is 4. Let's insert a 5. So take Q bracket 4 and set that equal to our number 5. And then increment the tail. All right, we have a potential problem. If I call insert again, it's going to try to store in element 5, because tail's equal to 5, and there is no element 5. We only have elements 0 through 4. We're going to write into something outside the array. That's a potential seg fault. But our queue is not full. Right, the 3 and the 1 have already been removed from the queue. 4 is the next thing to remove, so these 2 spots are still free. They've got stuff in them, but they're available for our queue. So if we want to insert something again, where should we put it? Yeah, put it back to index 0. So after we do this insert 5, we notice that the tail is equal to 5. We should actually change that to a 0. So that now the tail is sitting back here. So we can modify our insert routine. If t is equal to 5, set t equal to 0.
Alternatively, can we use the modulus?
Or we can use the modulus. Because since t is always positive, that's exactly what t modulus 5 is going to do.
Could you put that in the increment command? So
Or we could put it in the increment command. or it could be t plus 1% 5. Or we could combine all this together and say q bracket, no, we can't do it. We won't go that way. We could do q bracket t plus plus equals n, and then t equals t% 5. But we'll do that later. So some way to roll t over so that when it hits 5, it goes back to 0. All right, so let's insert some more stuff. Let's insert a 9. Well, our insert says take element 0, set that equal to 9. Increment the tail. Let's insert one more thing. So we'll insert a 2, tail's equal to 1. We put the 2 right here, and we increment the tail. All right, we just created a bit of a problem for ourselves. Because when we started off, the head and tail were 0. And we noted yesterday that if we add some things and remove some things, the head and tail may not be 0, but they may be equal to each other. And when they're equal, that tells us the queue is empty. But now the head and tail are equal to each other, and in fact our queue is full. Right, we've got a 4, 1, 5, 9, 2 sitting in our queue. But if we just say, hey, is head equal to tail? Yeah, I guess the queue is empty. We just wiped out our queue. So let's not do this last insert. Let's leave tail at 1. So our picture looks like this. So here's the thing. We have two options. If we insert and we end up with head equal to tail, we know the queue is not empty because we just inserted something. So we have to conclude the queue must be full. So if you insert, increment the tail, and then the tail is equal to the head, the queue is full. We could set a flag. And then when we want to do something, we can check to see if head's equal to tail. If they are, check the flag. That tells us if it's full or empty. It's a little bit of housekeeping. There's an easier way to deal with this, which is don't ever let the queue get completely full. So we have 5 spots in here. What we're going to say is you can only store 4 things in this queue. You're just going to waste 1 spot. It's a small price to pay for being lazy about coding. So when you insert, you're going to store at element t, increment t, roll it over, modulo 0. Before you do that, let's check to see if after we do this, head will be equal to tail. So we're going to add one more check in here. We're going to say if t plus 1 modulo 5 equals head, then the queue is full. I didn't have space for 2 equal signs. So if t plus 1 modulo 5 equals h, the queue is full. We're not going to do the insert. We're going to say, sorry, there's no space left.
So you make the rest of that just be an else?
I would just return here, actually. But yeah, otherwise you could just make that else do that stuff. And it's a bit of a cheat, but like I say, it's only 1 spot in memory that we're wasting. And it gets to be used as the queue moves around. All right, so at this point, if we tried to insert a 2, tail's equal to 1, 1 plus 1 is 2, that's equal to head. We're going to say, nope, can't insert the 2. Got to remove some stuff. All right, so removing, let's say we remove head's equal to 2, removing is going to give us a 4, and it's going to increment the head. If we say remove again, that's going to give us the 1 and increment the head pointer. If we say remove again, it's going to give us element 4, which is a 5, and increment the head. Same situation. If we tried to remove again, we'd be trying to get element 5. That's a problem. The clear solution here is instead of 5, we want this to go back to a 0. So same thing in removal. Look, I got some space. If h equals 5, h equals 1. 0. So both the head and tail are moving in this direction, and they get to roll back over to the beginning. So there's pseudocode at 3 lines for insert and remove. And how do we know if the queue is full? Well, that's the check we did up here. So we can say if tail plus 1 modulo 5 equals head, return true. Otherwise, return false. And how do we know if it's empty? Guesses?
Head equals tail.
Head equals tail. Right? And again, they may not be 0, but as long as head is equal to tail, the queue is empty. If tail plus 1 is equal to head, the queue is full. All right, last piece. How do we initialize?
Set head and tail to 0.
That's pretty much it. Because if we said head and tail equal to 0 or 1 or 3 or any other legal value, if we check to see if the queue is empty, it's going to say yep. And so in our insert routine, we check to see if the queue was full before we insert it. We should also do that in our remove routine. Check to see if the queue is empty. Otherwise, all kinds of weird things can happen. So you put in this code or you call your isEmpty function. So there's full implementation of a queue using a circular array. And converting this into actual legal C code and writing it up looks almost exactly the same. I made a few shortcuts, but it's basically C code. So something to note in here, right? When you remove stuff from the queue, that stuff is still sitting in the array. Right? We didn't actually take it out of there. We didn't replace it or overwrite it with something. We just changed our pointers to say that's no longer part of my queue. And so in memory, your array might look like this. And as you start inserting things, right, your queue is growing in this direction. At some point, this may be what your queue actually consists of. And then you pop off a few things, and now your queue might actually just be, you know, those 3 elements. And you push a few more things, and it might grow out to be these elements. And you might pop all of those off, and your queue might become completely empty. And now when you start adding some more things to your queue, it might look like that. And if you keep adding, it might take up those 2 elements. And if you add something else, it's also going to be this thing over here. So your queue might begin here and go all the way over there and wrap around. And all of this stuff is empty. So if you're coding this and you're looking at the actual array, it may not look like what you expect your queue to look like. right? Because we're in some sense reusing memory locations. But if you think of it as a torus, if you think of this end as being connected to this end, and it's just a big circular array. So if we looked at it from the top view, it might look like this. All right, that's all we're doing. So if this is element 0, element 1, I used one too many, but we'll ignore that. Right, so if I write something into location 9, the next time I write it's going to go into not location 10, but location 0. All right, so it's still doing something consistent. It's an array that's shaped like a circle. All right, so questions on that so far?
Yeah, when would we want to do a linked list version of this? So we have an infinite or somewhat infinite.
If you're doing PA3, you're going to want to do a linked list version. That's the quick answer. But the disadvantage of this is your array size is fixed. So it's got to be big enough that you won't run out of space. But maybe once in a blue moon you need 1,000,000 elements, but usually you only need 100. So do you allocate 1,000,000 and just kind of live with the extra space being wasted or not? So a linked list is very dynamic. So that might be one reason. A linked list is also quite a bit easier to code than all of this stuff once you understand how to do a linked list, which you do because you've done PA2 and PA1. So PA3 will be chopping up some of your PA2 code, making it a little less powerful, and it'll work well for these. Speaking of PA2, let me just do a really quick. Is everybody comfortable with valgrind for checking for memory leaks?
Yes.
Okay. I can't get to the server right now. So if your executable program is called, I don't know, let's say it's called main, all you got to do is say valgrind main. All right, so instead of just saying a.out, say valgrind a.out. Right? And it will run your program, and just pretend you're running your program normally. It'll give you a prompt. You can say I2, I3, D2, S5, P, all that kind of stuff. And when you're done and you say X and your program exits, you'll get a report from valgrind. And that'll tell you if you have issues or not. So I think you got to do something periodically with your web browser to kind of wake up the connection, which doesn't make me feel very comfortable saying that out loud. But at least it worked earlier. Give it 10 seconds. All right. Well, anyway, if you have a web connection, Linux server, so just valgrind main. And it'll either say, all blocks freed, no leaks are possible, that's what you want, or it will say, bytes and blocks in use at exit, leak summary follows, and it'll tell you about your leak. It can also give you warnings. You may see a whole slew of messages with lots of 8-digit hexadecimal numbers in them, and harsh language and stuff like that. If you're getting any of that stuff, right, something is wrong somewhere in your program. And your program may be running correctly. It may look like it's doing the right thing, but there's definitely an issue somewhere. And it can come, for example, if you allocate a block of memory and you use part of that block, but you haven't given it an initial value. It may be the initial value happens to be 0, and that's what you wanted to use. But if you don't actually set it equal to 0, valgrind will notice. And it'll say you're using an uninitialized block of memory. So you get lots of warnings that can help you. Ideally, you get all those warnings to go away. I'm not going to take off points for those warnings. I will take off a few points for a memory leak. But if you get those warnings, go look through your code, and there's probably something that's not quite totally clean. All right, so stacks. So again, we have an array. And let me just call this S. And the stack of plates at the buffet, right, we always put a plate on the top, and we take a plate off from the top. So the stack pointer, the top of the stack, is always physically the top of that stack of plates. But when we do that, something miraculous happens. When we put a plate on top, all the plates below move down a little bit. If we were to implement that in an array, the action would be, when we want to add something to this stack, we would put it into location 0. But before we do that, we'd copy what's at location 0 to 1. And before we do that, we'd copy what's in location 1 to 2. And basically everything in the array would move down one spot, making space for this new entry at location 0. And when we pop, we would read from location 0, and then we'd copy everything over to the right. Okay, that's a lot of memory movement. That's really expensive. And as your stack grows, it takes more and more operations. So we don't do that in software. Instead, we have something called a stack pointer. SP. And we're never going to move things in this array as we push and pop. Instead, we're going to put the first thing we push into location 0, but the next thing we push, we're going to put into location 1, and the next thing into location 2, and the next thing into location 3. And at that point, if we say pop, we're just going to return what's at location 3, and adjust things to remember that location 2 is where the top of the stack is, the last thing that we pushed. So if we pop again, we'll read from location 2. If we push, we'll push into location 3. So we're going to have this variable called a stack pointer. And we can interpret the stack pointer in two ways. The first one, so we're going to initialize stack pointer equals 0. We're going to say SP is where the next push is stored. So if stack P is 0, it means the next time we push, we're going to store at 0. If stack P, SP is 3, it means the next time we push, we're going to store at 3. So what does our push operation look like? Well, let's say we want to push a 2. We're going to store it at location 0, and we're going to increment the stacks pointer, just like we did with a Q, so that the next time we push, we don't overwrite the 2. So if we push a 3, we're going to store that at index 1, because that's where the stack pointer is pointing, and we're going to increment the stack pointer. So in general, our algorithm for pushing a number n is as follows. S bracket SP equals n, and then SP equals SP plus 1. So let's push one more thing. We'll push a 5, that goes into location 2. Stack pointer gets incremented to 3. All right, we pushed a 2, and then a 3, and then a 5. If I say pop, what number should I pop off? The 5. Last in, first out. The last thing we pushed on was a 5. That's the first thing we pop off. So we want to pop the 5. How do we find that 5 by using the stack pointer?
SP minus 1.
SP minus 1. So pop is as follows. First, we want to decrement the stack pointer, and then we use that to find the thing we want to return, the thing we want to pop. So we'll change the stack pointer to 2. We'll return element 2. We popped off the 5. If we say pop again, it will decrement the stack pointer to 1 and it'll return the 3. If instead we say push, it will push it into location 2 and it'll overwrite the 5. So this is our push, this is our pop. Again, we popped off the 5, it's still sitting in the memory. But we've adjusted the stack pointer to say, hey, our stack ends right here. This is not part of the stack, this is the location we're going to store something the next time we push. But it's still in there. So we can also interpret SP as SP minus 1 is where the next pop reads from. All right, we popped off the 5, let's pop off the 3. So we call pop, stack pointer gets decremented, we return element 1, that's the 3. Call pop one more time, stack pointer gets decremented, we read element 0, return the 2. Our stack is empty now. So how can we tell that the stack is empty by looking at SP?
SP equals 0.
SP equals 0. So if the stack pointer is 0, stack's empty. And if the stack is empty, then 0 is where the next push will be stored. And if we use this definition, minus 1 is where the next pop would read from, but there's no element minus 1 in an array. So in our pop statement, check for SP equals 0. Generally, before we pop, we check to see if the stack's empty. And if it is, we throw some kind of error condition. That's called a stack underflow. And if you've done 270, we've used this terminology in there. That's exactly what's going on. How do you know if the stack is full?
Depends on how big you made your array.
Exactly. Depends how big your array is. If your array can hold 10 things, then if all 10 things are filled up, and our stack pointer is pointing to the 11th thing, right, the stack is full. And there's nothing wrong with having a full stack unless you try to push. So in the beginning of the push, we should have some kind of check for full stack. So if the stack pointer is equal to whatever number corresponds to the last position in the array, then we can throw some kind of stack overflow error. And so your initialization of the stack is just SP equals 0. So we can initialize, see if it's empty, push something, pop something. That's your whole interface. All right, questions on this?
It's full.
Say what?
It's full.
Oh, yeah, it's doing is full. I wrote that sloppy because I don't really mean size of as in the C function call size of, but if SP is equal to, the number of things in your stack, if it's equal to the index of this last thing. But in practice, usually our stacks don't have a way of knowing if they're full because usually they're not implemented with an array, they're just implemented in memory. And we start at some memory location, and as we push things in, the stack pointer just keeps growing and growing until it hits something outside the bounds of memory, and then we get a stack overflow error. And it's usually a pretty severe error. If you do that on a PIC processor, it resets and goes back to instruction 0 and starts running from the beginning. But it sets a flag to let you know why it did that.
Already been that far.
Yeah. All right, so this is one version of a stack, but the choices that I made here were kind of arbitrary. Because here's an equally good way to implement a stack. I could increment the stack pointer first, and then use that to store my number. And my pop routine might read the element pointed to by the stack pointer, and then decrement the stack pointer, and then return that number that it read. And in this case, my initialization would be to set SP equal to -1. And that would represent an empty stack. Why? Because when I push, first I'm going to increment my stack pointer. If I'm empty, I'll increment from -1 to 0, and I'll store in location 0, which is presumably where we want to start. Unless you're designing a PIC processor, in which case they start at location 1 anyway, which is why there is no element 0 in the stack on the PIC processor. And then when we pop, right, we decrement after we've read the value. So our interpretation of SP is slightly different now. SP is actually where the next pop is going to come from, and SP plus 1 is where the next push is stored. So this is a post-increment, pre-decrement in this first version. Post-increment, after we use the value of SP, we increment. Pre-decrement, before we use SP. The only difference here is this is a pre-increment and a post-decrement. Equally valid. There's two other ways we can do this. We could start our stack down here on the left side, initialize the stack pointer to 10, and when you push, we could decrement the stack pointer, and when you pop, you could increment. So our push could be a post-decrement, and our pop could be a pre-increment, or our push could be a pre-decrement, and our pop could be a post-increment. Yes?
Is there a reason why you would want to switch around with those 4 options?
Yes. There's a lot of reasons. And it has to do with how your memory is organized. So if you're not using an array, if you're just using memory, we don't necessarily know how much memory your system has. It depends how much you go to Best Buy and buy and put into your laptop, right? So memory is often organized with a bunch of stuff in the beginning and a bunch of stuff at the end. And depending on how much memory you have, the size of this block can grow or shrink. And then there's dead space in the middle, where there's no memory. We don't know when we're writing our operating system where this address is going to be, but we know where this address is. So we would like to start our stack right here and grow in that direction. And so that would be a reason why you might want your pushes to move you to lower addresses. And this is why you see these numbers like 7FFF pop up so many times when you're looking inside GDB. You're probably looking at stuff that's stored on the stack. And it's using something like this kind of layout. But if you're on a PIC processor or an old Intel, 16-bit processor, you might just start from the beginning and grow, because you know how much memory is in the system or how much you expect to have in the system. So different ways to do that. All right, so we'll talk tomorrow when we go through PA3 about how this works using linked lists, and you'll see that it's easier than PA2. Our add function and our delete function basically just have to do something a little simpler than they do in PA2, and we can use that to implement stacks and queues. So we'll talk about that tomorrow.